An intricate docking maneuver in outer space. Human lives, millions of dollars, and a national space effort hang in the balance. A supersonic transport with 400 passengers aboard in the critical phase of the landing approach. The pilot's skill, experience, and preparation for any contingency are taxed to the utmost. Emergency. A runaway nuclear power plant must be deactivated. The fault must be quickly isolated and the proper shutdown procedure followed. Seconds are vital. The purpose of this presentation is to answer in simple terms these three questions. What is an analog hybrid computer? How and where is it used? How does it compare with other types of computers? Before we can understand the analog hybrid computer, we must first know the principles of analog computation. As we shall see, analog computers solve problems by simulation. An analog computer creates an electrical model of a physical system, greatly reducing the effort required by mathematical calculations or the expense of constructing physical models. Strictly speaking, the analog computer does not calculate answers to problems. Rather, by simulating the problem under study, it enables the scientist or engineer to simply measure any desired information about the physical system. The analog computer is constructed and programmed in such a manner that the mathematical equations which describe its operation are identical in form to those which describe the physical system. That is, the analog computer operates by creating an electrical analogy. The analog computer uses voltage levels to represent physical constants and variables. Problem values are scaled to adjust the magnitude of all voltages between a plus and minus reference voltage, usually either 10 or 100 volts. This reference voltage is designated 1 machine unit. In this example, an airplane flying at 20,000 feet, but limited to go no higher than 100,000 feet, would be represented by plus 0.2 machine units. Several types of devices display the computer variables. The digital voltmeter produces a 4 or 5-digit display. It may be connected to a printer or typewriter for a permanent record. The XY plotter draws on graph paper a line representing voltage variations. It may be used to plot an output voltage versus time, or, in cross-plot mode, one output may be plotted against another. The display scope is similar in function to the XY plotter, except that the computer output is displayed continuously on an oscilloscope screen. The effects of any adjustments to the computer program are immediately visible to the operator. The multi-channel recorder simultaneously records on a strip chart any set of the problem outputs. In addition, the analog computer has a readout system for rapid access to any voltage in the program. A modern analog hybrid system, the EAI 580 scientific computer. While at first it may appear complex, a closer inspection will reveal that it is made up of 5 basic analog components: summers, multipliers, potentiometers, function generators, integrators. These are the building blocks used to program the mathematical operations. By properly interconnecting these basic elements, virtually any engineering problem involving linear or nonlinear differential equations can be solved. Let us look at each of these components more closely. Summers are used to add or subtract two or more variables. In practice, electrical voltages representing A and B will be applied to the input of the summer. A voltage corresponding to their sum, A plus B, will appear at the output. The summer is also used for polarity inversion and amplification. Note that the actual output is minus the quantity A plus B. A change in sign is characteristic for most analog computer elements. Multipliers are used to multiply two variables. Multipliers operate instantaneously and continuously. That is, as soon as one or both of the inputs changes, the new product will simultaneously appear at the output, x times y. Analog multiplier elements may also perform division, squaring, and square root operations. Potentiometers multiply a variable by a constant, here represented by k. Parameter values and other constants are set into the computer program using potentiometers. This is a manually adjusted potentiometer. The programmer is setting it to a coefficient of 0.2, which means that the potentiometer output voltage will be 2/10 of the input. On some computers, operators set potentiometers automatically using digital or push-button controls. Function generators allow the use of experimental data in areas of a problem where the equations are not known or are not practical to program. The function generator is set up using data points, so that for every x input, there is a corresponding function of x output. An example of the use of function generators is in programming the lift characteristics of an airfoil for flight simulation. In this way, wind tunnel data can be incorporated into the program. Function generators may also generate the sine, cosine, or logarithm of a function. Lastly, and most important of the basic components, is the integrator. Integration is an operation of calculus. Although a full understanding of integration requires a study of higher mathematics, the concept of integration is familiar to us in many aspects of daily life. A pail being filled with water is a form of integrator. The amount of water in the pail corresponds to the integration of the flow rate during the time that the water is turned on. An automobile odometer is an integrator. It displays the distance traveled, which is a continuous integration of the speed of the car with respect to time. Similarly, if a voltage proportional to speed enters an analog integrator, the output will be a voltage proportional to distance traveled. The analog integrator has another important characteristic. A second input establishes the initial conditions at the start of the problem. The computer has three computational modes which are under push-button control by the operator. Initial condition mode is used at the start of a computer run to cause the integrators to assume their initial values. In operate mode, the computer simulation proceeds with all components operating simultaneously. Hold mode stops the integrators to allow the problem to be studied at any instant in time. For simulations in which human factors in the control loop must be considered, or when processing online data, real time is used. 1 second in the computer simulation corresponds exactly to 1 second in the physical system. However, it is not necessary to use real time. For example, in the simulation of a batch mixing process requiring several hours, it would be highly undesirable to run the computer that long. In this case, the programmer may speed up the problem for a fast time simulation. Several hours may be compressed into seconds. Many equivalent computer runs take place in the time required by the physical process. Conversely, the computer may be slowed to permit the study of rapidly occurring events. By appropriate programming, even a millionth of a second can be stretched to several minutes on the computer. Thus, we see that the solution time is independent of problem complexity. The programmer may select any convenient operating time. The analog computer, then, is composed basically of summers, multipliers, potentiometers, function generators, and integrators. Parameter and other constant values are put into the computer by means of the potentiometers. The time aspect of the problem is solved by the integrators. The integrators may be operated in real time, slow time, or fast time at the option of the programmer. The computer has three basic modes: initial condition, hold, operate. Now, let's put these components together to see how the computer works. This block diagram shows how several components could be connected together to simulate a trip that you might take by car. The accelerator pedal in this automobile simulator connects by a mechanical linkage to a potentiometer. The potentiometer output is a voltage proportional to acceleration. The acceleration voltage is the input to the first integrator. Its output is speed. The speed voltage could be connected to a speedometer display. In the block diagram, a voltage representing speed enters the input of the second integrator. As we have seen, the output is a voltage corresponding to distance. This could be connected to an odometer to indicate distance traveled. Thus, we have simulated an automobile. It can be started, stopped, and driven at a variety of speeds. We have made provision for the driver to continuously monitor speed and distance. By including engine power, weight, riding characteristics, and so on, we could further develop the realism and usefulness of the simulator. Ultimately, the analog computer could provide voltages to operate a visual display seen through the windshield of the simulator. The largest scale flight and space simulators use the same basic techniques. We have seen the programming of a simple model. The term analog hybrid is used to denote an analog computer which employs digital logic components to solve more complex equations. In addition to the analog components already mentioned, the analog hybrid computer is provided with comparators, gates, flip-flops, counters, timers, switches, and storage devices. These logic components make possible the solution of engineering equations in an automatic or iterative manner. Analog hybrid offers considerable computing advantage. The logic elements of the analog hybrid computer can be programmed to cycle the computer through a sweep of critical parameters. In this manner, for example, partial differential equations may be solved. A problem solution can be optimized by using the results of one computer run to automatically change the inputs until a best answer is found. And finally, the decision-making capability of the analog hybrid computer enables it to rapidly and automatically explore boundary values and stability areas, such as in this plot of Matthew's equation. To illustrate how the analog hybrid computer does this, here is a functional block diagram of the program. On the left of the diagram, an iterative timer generates an initial condition operate cycle many times each second. The system parameters A and Q are established for each cycle by a track store circuit. The particular values of A and Q for each run determine the position of the plotter arm and pen. In the center block, the analog circuits are programmed to operate on the inputs according to Matthew's equation. The output oscillations may be stable or unstable, depending on the values of A and Q. The output of the analog block connects to a stability detector, which uses comparators to decide whether the oscillations have exceeded certain limits. If the oscillations remain within bounds, the system is considered stable and the pen remains down. If the system is unstable, however, a cycle abort signal is generated by setting a flip-flop and the pen is lifted from the paper. The timer then causes A and Q to increment and a new run is begun. With this technique, thousands of values are tested automatically in only a few minutes. In a similar manner, space scientists use the analog hybrid computer to determine favorable launch times for orbital flights. Today's engineering problems are many. The complex requirements of modern technology and the demands of a competitive economy do not permit the use of trial and error with the actual system. Today's engineer is called upon to design a better product, and he must be able to do so quickly, efficiently, and economically. For this purpose, the analog hybrid computer is ideally suited. Whether it be a desktop model such as the EAI 380 or a larger, more powerful computer such as the EAI 7800 scientific computing system. Let's take a typical problem which might confront you as an engineer and see how you would solve it on an analog hybrid computer. We are going to investigate the design of a wheel and shock absorber system, like the system on an automobile or the landing gear of an airplane. Our aim is to study the elements in the system so we can choose values for the best performance. An aircraft landing gear is mechanically complex, so let's reduce it to its simplest elements. To program the computer, we must first build a mathematical model of the system. And here we see that we are concerned with an exchange of energy between three elements. The first element is a mass. When the mass is in motion, it stores kinetic energy. The mass resists a change in velocity with a force proportional, by Newton's second law of motion, to the product of mass times acceleration. We will denote by F1 the force required to overcome the inertia of the mass to accelerate it by an amount x double dot. In calculus notation, x double dot is the second derivative of distance with respect to time. X double dot simply means acceleration. The force equals mass times acceleration. The second element is a spring. The spring is a storage device capable of accumulating potential energy. The amount of force required to extend or compress the spring a distance, x, is given by Hooke's law as a spring constant, S, times x. We denote by F2 the force required to displace the spring. In this problem, there will be an initial displacement of the spring due to the weight of the mass. Our measurements of displacement will be in reference to this equilibrium point. Also, we might desire to introduce constraints on the excursion of the spring due to mechanical stops. The third and final element in the system is a damper, here represented by a piston-type shock absorber. In the exchange of energy between the spring and the mass, the damper absorbs part of the stored potential, causing the motion of the system to eventually come to rest. We shall assume the force required to move the damper is directly proportional to the speed we attempt to move it. We would express this as F3 equals d x dot, or force equals damping factor times velocity. In a practical shock absorber, this linear relationship might not hold true, in which case we would gather experimental data and insert these in the program by means of a function generator. Put the three elements together, and we have a mathematical model of the spring mass damping system. In this system, the sum of the forces F1, F2, and F3, taken with regard to direction, is equal to 0. This is always true, regardless of whether the system is in rapid motion or at rest. This force balance gives us the computer equation mx double dot plus dx dot plus sx equals 0. Here is a computer program for this equation. The programming technique is straightforward. First, solve the equation for the highest order derivative. Second, assume the highest order derivative x double dot is available and integrate enough times to produce the speed and displacement vectors x dot and x. Third, use potentiometers to set in the problem parameters m, d, and s. Also, establish the starting values for speed and displacement with potentiometers connected to the initial condition inputs of the integrators. Fourth, combine appropriate values to yield the equality expressed by the program equation. Connect these to the x double dot starting point by means of a feedback loop. This completes the diagram. The actual programming of the computer is simple. Using the diagram derived from the system equation, interconnect the components at the computer program panel. Place the program panel on the computer. The program panel, it should be noted, is removable. Programming it off the computer does not consume valuable machine time and allows other problems to be run in the meantime. After a problem has been run, the program panel may be stored for future use. Next, set the potentiometers to the system parameter values, and the problem is ready to be checked and run. The computer solution as displayed on the XY plotter. The relative displacement of the landing gear system as it contacts the ground is shown as a function of time. Note that for the values chosen, the solution is a damped oscillation. Now, by simply turning a potentiometer, you can effectively change the tension of a powerful spring. The effect of changing each of the problem parameters, mass, damping, and spring constant, can be studied by drawing a family of curves. Questions such as, what happens if both spring tension and damping are increased as the mass is decreased, can readily be answered. The response of the system to various disturbances, transient, cyclic, and random, can be analyzed and predicted. The best values for a given set of design criteria can be chosen. Of great importance to the engineer is the fact that the graphic presentation, combined with the ease of making adjustments, enables him to develop a feel for the system under study. He can bring his intuitive powers to bear on the problem. This is especially true in the case of analog computers equipped with a repetitive operation display. In repetitive operation, hundreds of computer runs are made each second, and the results are displayed continuously, as shown here on an oscilloscope. By changing the potentiometer settings, the operator can experiment freely and immediately see the results. While we have been studying the spring mass damping system in relation to the design of an aircraft landing gear, even this simple simulation has wide applications in many fields: electronics, chemistry, biology, mechanics. In fact, wherever a scientist or engineer is investigating a system in which there is an exchange of energy, this basic problem will occur. At this point in our study of the analog computer, it would be beneficial to compare it with other types of computers. To first summarize the basic analog concepts. Analog computer variables are voltage levels between plus and minus reference, normally measured to 4 decimal places, and are directly proportional to the problem variables. Analog operation is continuous, with all components operating simultaneously and in parallel. The computer simulates the system under study. It may be operated in real, fast, or slow time. The analog hybrid computer has the same characteristics with the addition of digital logic elements for decision-making and control. The analog hybrid computer may be programmed to automatically find a best solution to a given problem. The digital computer as we know it today is an electronic calculating machine. The operations it performs are essentially the same as counting the digits on your hand, except that the digital computer uses electronic components for storage and counting. Characteristic of the digital computer is the fact that the variables are discrete. That is, numbers are exact and distinct. Digital numbers are expressed in the binary system, either 0 or 1. There are no in-between values as with the analog computer. This gives the digital computer excellent precision. The digital computer contains banks of memory cells for storage of the binary numbers. The precision of the digital computer, combined with its massive memory, makes it well suited to bookkeeping and data processing, as well as arithmetic calculations. The operation of the digital computer is sequential. This means that the answer must be calculated one step at a time, just as you would if you wanted to multiply 2 numbers on scratch paper. The digital computer, however, has one considerable advantage over pencil and paper. It can perform each arithmetic operation in a few millionths of a second. This means that even the most tedious calculations can be accomplished in a short period of time. The solution time is dependent on the complexity of the problem. Since a great many arithmetic calculations are necessary for a digital computer to solve a simulation problem, the real-time aspects are often lost in this step-by-step procedure. Instructions and data are given to the digital computer by means of punched tapes, punched cards, magnetic tapes, or directly from the operator's typewriter keyboard. Digital answers are usually in the form of printed sheets, which of course must be read and interpreted. A third type of computer is the hybrid computer. The field of hybrid computation will be covered in depth in another presentation. We mention here only the basic hybrid concepts. The hybrid computer combines the best features of both analog and digital. It is, in fact, a computing system made up of a digital computer and one or more analog computers, with a means provided for exchange of information between the computers. One of the most important parts of this system is the hybrid software used to program and control the system operation. EAI has pioneered in the development of complete hybrid systems. In a typical space simulation, a hybrid system uses the digital computer to maintain precise calculations of the slowly changing orbital position of the flight. The analog section continuously simulates the controls and orientation of the space vehicle. Together, they give the greatest possible speed and accuracy. To summarize, then, the analog computer solves by simulation. The operation is continuous, with all components operating in parallel. The solution time is independent of problem complexity. Analog hybrid employs logic elements for decision-making and control. Analog hybrid computers are used primarily for solving dynamic problems. In this presentation, we have discussed the analog hybrid computer. The analog computer is a powerful and useful engineering tool which each day sees new applications and advantages. Analog hybrid computation is playing an important role in the future of aerospace nucleonics, biomedical, electronics, and all areas of scientific endeavor. Truly, tomorrow is being explored today on the analog hybrid computer.